Hi, I'm John Ellis. I'm from Optics for Hire. I'm with Vasily Kornachik, and today we're going to talk about depth of field. This is an important optical property which a lot of imaging systems need to specify. And Vasily, who is a physicist and engineer at Optics for Hire, as well as the director of our Minsk office, has prepared this short presentation that explains some of the physics behind depth of field. Hi, Vasily. How are you?
Hi, I'm good.
So first, let's start with some basic definitions. And for the layperson, the depth of field is basically it's the area in which an image appears to be in focus. And in focus means that the optical resolution of that image or that object is as high as possible. And in some systems that we've designed, you want the depth of field to be as large as possible because you want a lot of things in focus. And we've also worked on optical systems where you want to have a very small depth of field because you didn't want items outside of the range you were interested in to be in focus. So Vasily, on this first slide, you're introducing a concept called the circle of confusion. And on the left here, you have your object that you're looking at. Here is the image plane where an eye would be, or an image sensor. And you have these different areas called out, the depth of field and S. And so what are these different distances? Here we have S. What is S in this chart?
The distance of image.
Image distance, okay. And this is the diameter, is this an aperture?
Diameter, aperture diameter.
Aperture diameter, okay. And then you have the diameter of the circle of confusion. And as I'm looking at this, it looks like the larger the depth of field, the larger your so-called circle of confusion would be. Is that correct?
Yes, correct.
Okay. All right, so we have depth of field, aperture, object distance. All right. So here are some formulas which to me look pretty complicated. And you've got a couple different formulas. Now, tell me about this top formula.
This formula shows a dependence of depth of field from parameters of system and object in image position. F is focal length of optical system. S is distance to object. N is numerical aperture, and DC is circle of confusion.
Okay. All right. And then this second formula here, why do you have two formulas? It says when S, this, go ahead.
In mostly of cases of using of optical system uses with very long distance to object. And for very long distance object, when distance to object much bigger than focal length of system, the formula for depth of field converted in more simple kind.
Okay.
With just several values.
Got it. Okay. So if the object distance is much bigger than the focal length, which for most optical systems it is, you can use this formula to determine what the possible depth of field, meaning what the possible area for which the system can be in focus is. Okay, great. Let's go to the next slide. So now you're talking about circle of confusion, and you say there are three different things that create this so-called circle of confusion: diffraction, point spread function, aberrations, and also in an imaging system or camera type system, the size of the pixel. And those are going to help determine what depth of field you can achieve. So let's look at this first formula. So here we're talking about diffraction. Can you explain this to me a little more?
All of optical system possess limited aperture. A limited aperture in physical optics provides diffraction. Diffraction has some diffraction pattern which has some size. This size is well-known formula, and this size of first or maximal is named as airy disk size. In this case, diameter of airy disk corresponds to a cycle of confusion.
Okay. Okay, so the diffraction limit in some systems can be what creates the size of the circle of confusion. And the larger the diffraction limit, the bigger the circle of confusion, or have I got that wrong? If the
bigger aperture,
yes.
the bigger aperture provides smaller circle of confusion.
Bigger aperture, smaller circle. Okay, so that's why with a small aperture lens, you can have a larger depth of field. But when you start to get to large aperture lenses, which are collecting more light, the depth of field is reduced. Have I got that right?
Sometimes photographic lenses has aperture stop iris diaphragm, and it well-known fact that if you would like to increase the depth of field, you just make aperture stop smaller.
Mm-hmm.
You just make diameter clear diameter of objective smaller, and it help to reach bigger depth of field. This is just connected with influence of diffraction.
Okay. Okay. Thank you. All right. Let's look at the next one now. Aberrations. So tell me a bit about how aberrations can impact circle of confusion and depth of field.
Aberration just result in blurring of point image. Point image going to increase and convert it to some spot. This slide shows influence of spherical aberration. Spherical aberration has some best focal position, and in this slide it corresponds to waste of some waste which connected with spherical aberration. This diameter, the smallest diameter of beam, we can just take as diameter of cycle of confusion.
Got it.
So
okay.
the bigger aperture, the bigger diameter of cycle of confusion, the more the bigger depth of field for such lens.
Okay. Okay. All right. And then you have a third reason, which is sensor resolution. And if I understand it correctly, sensor resolution, aberrations, and diffraction, those three are not multiple. It's your system depth of field is going to be limited by one of these. Is that right? Just one of these will determine what it is. And in different systems it might be different, but sometimes your depth of field would be limited by sensor resolution, other times it would be limited by aberrations. Is that correct?
Yes, that's correct.
Okay.
But sometimes, for example, for optical system with high image performances, for example, microscope lens, the depth of field just has as sum of diffraction and cycle of confusion and sensor cycle of confusion is just sum of
The sum of those two.
factors.
Okay.
Yes.
I see. Okay. All right. So in some high resolution systems, it could be the sum of sensor resolution and diffraction. Okay. Okay. All right. So this is your final explanation or final detail about sensor resolution and how that impacts it. So we have here pixel size. And this pixel size to me looks like it's similar to the size of the circle of confusion. And diameter of circle of confusion equals the pixel size. Okay. Okay, so a smaller pixel size so does that mean a smaller pixel size has a smaller depth of field or
yes, smaller
yes.
yes.
Okay, smaller pixels means smaller depth of field because your image doesn't appear in focus, and larger pixels allow you for better depth of field. Okay, great. All right. So here in summary, all optical systems, the depth of field is going to be restricted by some of these kinds of limitations. And it could be F number, it could be object distance. But in a real system, there are aberrations, aperture values, pixel sizes, all of which have to be taken into account when you're determining what depth of field is achievable. So, for every application, there's a different need for depth of field. And as I said at the beginning, sometimes it's small depth of field desired, sometimes it's bigger. But you can see the balance of these different optical properties defining what is possible or isn't possible. So Vasily, thanks very much for putting together this presentation. It's been really helpful to me and hopefully folks who are watching this. And I'll talk to you later. And thanks again for putting this together. Thank you.
Thank you. Bye.
All right.